Okay, greetings. It's about 45 minutes since we got out of class, or about an hour since we got out of class. I've been taking care of some administrative things. Some really cool stuff happened in the class today. I kind of like this new way of doing things. I know some of you might be getting frustrated or something like, but trust me, there's three phases of learning physics. First phase, most of you got past this with the Coulomb's law and the electric field, where you're totally baffled. You're into the second phase, which is the most important, and that's totally frustrated and pissed off. Okay, if you're frustrated or pissed off, guess what? You are learning physics, and that is a good thing. All right, and then pretty soon, all of a sudden, it's like, aha, I got it. Now, something came up with today's problem where I told Gage a wrong answer, and I want to clarify that right now. Here was our basically our problem, and we saw that what we had to do was I've kind of expanded, so my hand is going to be this big hairy thing moving in here. But we saw that the forces here on Q1, he's being pulled this way, and he's being pulled this way. So this is the force, and then we had a notation issue with another student. I can't remember his name, and I apologize. He knows who I'm talking to. Where I said this is a force on one, he's going, well, isn't this the force caused by two on one? I said, no, I think it's the force on one caused by two. Doesn't matter. We've got it down, right? Oh, this would be three, so I still had it wrong. Yeah, my credibility sometimes just goes right out the frickin' window. And we can tell this is a larger charge, closer in, so this force is going to be bigger. So we know we're going to have a positive answer. And most of you figured it out that F13 is equal to K. And like I said, we like to use negative 4.0 times 10 to the negative 6. Sometimes I don't understand your questions. Because somebody said, "Do we need to put this into coulombs?" It's like, yeah. Or can we do it in microcoulombs? No, you can do it in micro. No, 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 no. You got to put it in coulombs. So I got to listen to the questions that you guys are asking because they're important. All right, divided by uh, uh, 1.3. Oh, he's divided by 0.15 squared, and I think that came out to be like 11.4, right? I I I think. Um, hell, let's type it in here real quick. Yeah, but I really have to get to the point here. So we got 9 second e to the 9 parentheses, uh, and then remember we're just doing the magnitudes of the charges. Not we don't put in the 4.0 second e to the negative 6, and oh no, he's 3.0. See, there's so much. This is so fraught with peril. And then 7.0 second e to the negative 6 divided by, and I like to even go ahead and put that in parentheses, 0.15 squared. Sometimes you'll forget the squared in the heat of battle. And yeah, that came out to be 8.4 newtons. Okay? And I had another great question too. Is why is the electric field newtons per coulomb? I don't get how that works. And I'll show you that in the next video, is because this is going to require two videos to go through this. And then so F12, I think once the force of 1 on 2, we came up with that was negative 2.7 newtons because it was pointing that way. Gosh, dang it. All right, and then we came up with that the sum of the forces was equal to 5.7 newtons. And here's the thing. Okay, so the sum of the forces. So let's go ahead and let's put Q2 here, Q3 over here, and say, hey, the forces right here at this point is 5.7 newtons. Look what happens when I put a little point charge right here of 3.0 microcoulombs. The electric field is equal to F over Q naught. So I'm putting this little Q naught. So I'm going to say this is my Q naught. I'm just putting that little charge in there. And look what happens. I get 5.7 divided by that charge of, what the hell was it? 3 second e to the negative 6. Bang. And this equals 1.9 times 10 to the 6th newtons per coulomb. And that is what you should have gotten. That's the electric field around that point. That's the electric field that is acting on that charge at that point. And I made you do it the long way though. I made you do this electric, and notice what we have. We've got a force, which is in newtons, divided by a coulomb. So we've got newtons per coulomb. But if we just want to do a point charge, so if we look at Q2 here, and then find the electric field, and since it's negative, its E field is going this way at 0.2, 0, and so E2 was equal to negative K, Q2 negative 4.0, the magnitude of times 10 to the negative 6 coulombs divided by 0.2 squared. And then E3 is pointing this way because its electric field's coming in. So Q3 is equal to K, and it's positive, and the magnitude of the charge, 10 to the negative 6th, divided by 0.15 squared. And when we added those two together, this one was small. This one came out to be like 900,000 newtons per coulomb. And this one came out to be, E3 came out to be 2.8 times 10 to the 6 newtons per coulomb. Subtract the two, you wind up with 1.9 times 10 to the 6 newtons per coulomb. So, Gage, you were correct. You were absolutely right. All you had to do was, hey, can't we just take the net charge and divide? I was going, oh, because I hadn't worked it out yet, I didn't want to say. Perfect. That's absolutely perfect. All right. That's enough for that one. That's video 1. Now we'll look at some of your